All right. So, a couple classes ago, we talked about sampling distributions of sample proportions, or p-hat. Today, we're going to be looking at what if we are looking at a sampling distribution of our sample means. So that kind of just repeats what we talked about. So, for our sample proportions, that's when we were looking at categorical data. Now we're going to be looking at quantitative data. Right? And oftentimes the measure that we will use for quantitative data is a mean. Right? A lot of times you'll hear that in the news talking about, the average, blah, blah, blah. All right? That's what we're looking at today. Now, we're going to start with a population distribution. So our histogram here is the population distribution of all of the Algebra 1 Unit 2 quiz scores. And as we can see, the mean is in blue and the median is in pink, and those are right on top of each other. We have a roughly normal distribution here, spread going from 0 to 32. Now, what if we wanted to make a sampling distribution of this? So not take every individual, but now take groups of 2 individuals and find their means, and do that for every possible combination of 2 students. What would that look like? Well, if we take an SRS of that, and an SRS is kind of obsolete because it's every single group of 2 students, and plot the sampling distribution for all 10,000 of those samples, this is what the distribution would look like. Take a moment and compare it to our sampling distribution for populations. Okay. What if I then take a sampling distribution for every group of 5 students? Well, and then take the average of their test scores. So we're grouping 5 students together, taking their test scores, grouping the next 5 students together, taking their average of their test scores, and then doing that for every single group of 5 individuals and plotting all of the averages of those 5 students' test scores. That's this distribution. Take a moment. Compare it to our mean, or compare it to our sample of 2 individuals and our population. All right? Now what if I take all the possible groups of 16 and find the average of each of those groups of 16 students and plot all of those averages? This is what this distribution would look like. And then the same thing for groups of 25. Take a moment and think about what was the shape of our original population distribution. Well, it was normally distributed, right? So what happened to the shape of the sampling distribution as our sample size increased? Well, it stayed normal, right? Didn't really change at all. All of those were normal. But what about the variability? Let's take a look. So this one up here at 16, right? It's a little less spread out, is a little more spread out than this one at 25. 5 is more spread out. 2 is even more spread out. And our population distribution is even more spread out. Interesting. Let's take a look at another population now. So this is the Unit 3 quiz. So a little bit more difficult, which means I have skewed right data. Right? I have a skewed right data. So blue being the mean, our blue vertical line down here is our mean. That's our median. Right? The mean gets pulled towards the tail, if we remember. Yay, reviewing concepts. All right, now let's take a sampling distribution and plot all of our sample means. How about for 2? Interesting. Again, feel free to compare that back to our population distribution. What about for a sample size of 5? Interesting. Then we can compare it to our sample distribution of 2. What about 16? Something interesting starting to happen here. And for 25? Once again, something interesting seems like it's happening there. So what was the original shape of our population distribution? Well, it was skewed right, right? We had a lot of data on the left-hand side, and then our tail went to the right, so skewed right. What happened to the shape as our sample distribution, of our sampling distribution as our sample size increased? We got closer to being normal, right? That's extremely powerful for us. Right? Skewed right distributions we can kind of figure out, what the probability is under those curves, but for normal distributions, we can easily find the probability that we're under those curves. What else did we notice as the sample size increased? Well, our spread decreased, right? There's a lot less spread, and it became more normal. So that number 2 concept, right, where even though we have skewed data, the sampling distribution is going to be normal, or get closer and closer to being normal as we increase our sample size, is a really important theorem called the central limit theorem. Right? So that states as our sample size increases, the shape of the sampling distribution of sample means is approximately normal. So for our sample distribution of sample means, the shape is going to be normal if the population is normal, no matter how large of a sample size we take. Think about that again. If I'm drawing from a normal population, right, for the Unit 2 quiz, that first quiz that I talked about, right, no matter what sample size I have, the sampling distribution is still going to be normal. Larger sample sizes is just going to let us decrease our variability. However, if I have a skewed data, or I don't know what the shape of the population distribution is, then as long as I take a large enough sample size, the sampling distribution will still be approximately normal. Right? Notice that I put approximately normal. It's not going to be perfectly normal. Now, where's that cutoff? Well, we say as long as our sample size is greater than or equal to 30, no matter how skewed our data is, no matter how skewed our population distribution is, the sampling distribution will still be approximately normal. Okay? This is not to be confused with our law of large numbers from Unit 4. So the law of large numbers said that if we're finding an experimental probability and we do many, 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 many trials, that proportion should be getting closer and closer and closer to a single value, right? What does a 50% chance of heads mean if I flip a coin? Well, it means that after many, many, many tosses, the probability will close in or get closer and closer to 50% heads. So actually that law of large numbers is going to help us for our center, right? If we take larger sample sizes, that means that the single value that we are getting closer and closer and closer to is actually the mean of the population, the true mean of the population. So the mean, let's talk about this notation. This means the mean of a sample distribution of sample means is going to be equal to the mean of a population. Now, why do we use mu here? Well, because we are plotting every single possible sample proportion, right? So this is the population for this is, sample mean. The population for this is all of the possible sample means. The population for this is all of the students, okay? And these two will be equal to each other. The spread, well, as our sample size increases, our variability will decrease. So we use standard deviation since we're talking about a normal curve, and that gives us a little bit more information. And so our standard deviation of our sample distribution of sample means is going to be equal to our population's standard deviation divided by the square root of n. So as you can see, n's in the denominator, so as we increase sample size, our standard deviation decreases. This is only going to be true if our 10% condition is met. So if our population size is at least 10 times our sample size. Okay. So suppose that the number of texts sent during a typical day by randomly selected high school students follows a right-skewed distribution with a mean of 15 and a standard deviation of 35. Assuming that the students at our school are typical testers, so all of you are typical testers, how likely is it that a random sample of 50 students will have sent an average of at least 10 texts? So we're trying to see what's the probability that I could take a sample of 50 students and their average will be 10 texts or more. Right? Since we are focusing on a random sample of n that is greater than 1, we're going to be using a sample distribution to sample this problem. So if we were just using 1, then we would just look at the probability distribution. In this case, we're looking at more than one student, so we've got to use a sample distribution. We're also talking about an average, so that tells me that I'm going to be using a sample distribution of sample means. Right? So let's walk through the four-step process for this. So the first thing we need to do is our state. And in our state, we are going to, just like we did for proportions, first define what our x bar is going to be. And I realize that that should be an x bar. I will make sure to change that on the actual PowerPoint so that you have that correct. But we're going to let x bar equal the average text from a sample of 50 students with our with our probability statement being that we're trying to find the probability that an x bar is greater than or equal to 10. And that should be the correct in the key, by the way. For our plan, well, we need to check our conditions. We need to make sure that our distribution is approximately normal. We need to make sure that we've taken a random sample. We need to make sure that we meet that 10% condition. So for our normal, well, the first thing we should always look for normal, and I know I haven't done it here, and we'll talk about why, is to see, is my population normally distributed? Because if my population is normally distributed, then it doesn't matter what sample size I took. That my sampling distribution will be approximately normal. Well, if we read up here, we can see that, nope, we have a right-skewed distribution. So I need to check to see, is my sample size then greater than or equal to 30? Well, I've sampled 50 students, and 50 is in fact greater than or equal to 30. I know, new information here. So that means that our sampling distribution of sample means is going to be approximately normal. Okay. Next thing I need to check is, did I take a random sample? Well, yeah, it states that a random sample of 50 students is taken. So we do meet the random condition. And the last one is the 10% condition. We need to show that the population is greater than or equal to 10 times our sample. Well, in this case, I don't tell you what the population size is, but I think it's safe for us to assume that there are more than 500 high school students in our population. Therefore, our standard deviation equation is going to work. So if I don't give you the population size, then just assume that we meet that 10% condition. So now that we've checked those conditions, we know that our sampling distribution is going to be approximately normal. We know that the mean of that sampling distribution, sorry about the fuzziness here, is going to be equal to 15 because that's what the mean of the population is. Right? And our standard deviation, should also have a bar over there, I'll make sure that that's corrected in the PowerPoint, but on the key it will be. So our standard deviation of this distribution is going to be equal to the population standard deviation over the square root of my sample size. Okay. In our case, our population standard deviation was 35, and our sample size was 50, so our standard deviation is going to be about 4.95. From there, well, this is a normal curve, so I get to just use normal CDF here, right? With my lower bound being the average of 10, my upper bound being infinity, but we can't do that, so 9999. Our mean being 15, and our standard deviation being 4.950, making sure that we will label those because we're good AP Stats students. We find that that's about 0.844. So now we conclude in context. So the probability that a sample of 50 students will send an average of 10 texts is 84.4%. Think about, again, how powerful that is. The fact that we know the probability that in a population where the average is 15 and the standard deviation is 35, that the probability that an average 50 students will have an average of 10 texts is 84.4%. We're going to use this a lot when we get into hypothesis testing and confidence intervals next unit. All right, in this case, we are looking at how likely is it that a random sample of 50 students will have sent less than a total of 1,000 texts. Well, that's a total. We can't use a total when we're doing this because we don't have a sampling distribution of totals. We only have a sampling distribution of sample means. So we need to convert this into a mean, which is what I've done here, right? So anytime where I give you a total, you need to convert it into a mean and then do the four-step process. So for the next two questions, I'd like you to try those on your own. And again, you can check the key to see whether you got the right answer or not. Right? Hope you found this helpful and somewhat interesting. I think this unit is fascinating personally. Have a wonderful day.